Have you ever taken apart a flashlight or just wondered how your phone works? Well, it all starts with the most fundamental building block in all of electronics, the series circuit. And today, we're going to pull back the curtain and see exactly how it works. So let's kick things off with a really simple question. Imagine you've got a battery, a couple of light bulbs. What's the most basic, no-frills way you could possibly hook them all up to get them to work? Yep, you probably guessed it. The answer is a series circuit.
Visit youtube.com/avidsystem and don't forget to subscribe.
So what in the world is a series circuit? Well, the best way to think about it is right here on the slide. It's a single path highway. There is only one road for electricity to travel. And you know what? That one little detail makes all the difference. All right, here's the more official textbook definition. A series circuit is when you connect components end to end. All that really means is you connect the end of one part to the beginning of the next, and then the end of that one to the beginning of the next one after that. You get the idea. It creates this one single unbroken loop for the electricity to flow. And this is the perfect way to picture it. If you think of electricity as traffic, a series circuit is like a one-lane road with no exits. Every single car, every little electron, has to follow the exact same path. There's just nowhere else to go. Once you really get that single path idea, you've unlocked the secret to understanding the 3 golden rules of series circuits. So let's jump into the first one, which is all about the current. This brings us to our first absolutely critical rule. The flow of electricity, what we call the current, is the same everywhere in the loop. It doesn't get used up by the components. If you measured the current at the beginning, the middle, or right at the end, you'd get the exact same number. It's like everyone is marching in perfect step. And the math for this? It couldn't be simpler. The total current, which we call IT, is just equal to the current flowing through the first component, which is equal to the current through the second, and on and on. It's just a simple chain of equal signs. Easy, right? Okay, on to rule number 2. If the current is our traffic, then resistance is kind of like all the obstacles on that single-lane road. Speed bumps, toll booths, anything that slows things down. So what do you think happens when you keep adding more and more obstacles to that one lane? Well, it's pretty intuitive, isn't it? They just add up. Every single component you add to the chain adds its own little bit of resistance to the grand total. Each new obstacle makes it just a little bit harder for all that traffic to get through the entire circuit. And again, the formula is super straightforward. The total resistance, RT, is just R1 plus R2 plus R3, and so on for however many parts you have. No tricks here, just simple addition. All right, we've got it. Current is the same everywhere, and resistance just adds up. That brings us to our third and final golden rule, which is all about voltage. Now, if voltage is the push, the energy that's actually moving the current, what happens to that energy along our single-path highway? And here is the last piece of our puzzle. The energy gets shared. I want you to think of the total voltage coming from your battery like a big pizza. Every component in the circuit gets to take its own slice. It drops or uses up a portion of that total energy. The math makes perfect sense with our pizza analogy. The total voltage from the power source, VT, has to equal the sum of all the little voltage drops across each part. Add up all the slices and you get the whole pizza back. It always has to equal the total you started with. This chart makes it totally clear. Let's say our power supply is 12 volts. You can see exactly how it's being shared. This first resistor takes a 4-volt slice. The next one is a bit hungrier. It takes a 6-volt slice. And the last one just needs a little 2-volt piece. And what happens when you add them up? 4 plus 6 plus 2, you get 12. It adds up perfectly every single time. Okay, so you're probably thinking, this is all cool theory, but what is it actually good for? Well, it turns out this whole voltage sharing thing is actually a superpower, and it leads to one of the most useful applications of a series circuit. And that superpower is called a voltage divider. So check this out. Let's say you have a 9-volt battery, but the little chip you're trying to power needs exactly 5 volts to work properly. What do? Well, you can build a series circuit with just the right resistors to create that perfect 5-volt drop. And then you can tap into the wire right there to get the precise voltage you need. It's a seriously handy trick. And we can figure out exactly what that voltage will be by putting all our rules together. First, you add up the resistances to get the total. Then you use that number to find the circuit's current, which, remember, is the same everywhere. And finally, You use that current to calculate the specific voltage drop across the one resistor you care about. See, it's just the three rules all working together. So let's just boil it all down. If you're going to remember anything from this, let it be this little cheat sheet right here. In a series circuit, the current is the same, the resistance adds up, and the voltage is shared. That's it. That's the core of it right there. So we have totally mastered the single-path highway. We know exactly how it works, but that brings up a really interesting question, doesn't it? What would happen if we gave the electricity a choice? What if we built an exit ramp or a whole new lane for the traffic to travel down? Well, my friends, that is a whole other story and a great topic for our next explainer.
Thanks for watching.